Hello friends, I'm going to start algorithm. This is a very important subject for computer science related students. Many students face difficulties in algorithm and this subject is also important in terms of competitive exams and placement perspective. I'm going to cover algorithm in a simpler way so that you can learn from basics. Today we are going to start introduction to algorithm. The overview of our today's lecture is first we are going to study with few definitions, then analysis of algorithm, then we will start asymptotic notations and types of algorithm. Let's start with few definitions. Do you know what is algorithm and what is program? Algorithm is step-by-step process to solve a specific problem. For example, if someone tells you to write an algorithm to add two integers given by a user, then you will write step 1 is to declare a variable. Step 2 is to take input from user and store it into a variable. Your step 3 is to apply addition operation and your last step is to print the final value. These steps are the algorithm to add two integers. Now, program is the implementation of algorithm in some programming language. For example, if you have an algorithm to add two integers, then you just have to follow the steps in any programming language to take input from user, adding the value and printing the final value. So the step-by-step process to solve a specific problem is algorithm and implementation of an algorithm is a program. Now we are going to learn time and space complexity. Before learning time and space complexity, do you know why do we need to find complexity of an program or algorithm? Yeah, we need complexity to get an independent measure of efficiency of the program or algorithm. Now we know why we need complexity, but how can we find complexity, like on what basis we can measure complexity? Here comes the use of time and space complexity. The program needs some space or time for implementation. Time complexity is a function describing the amount of time an algorithm takes in terms of the amount of input to the algorithm. Space complexity. Space complexity is a function describing the amount of memory an algorithm takes in terms of amount of input to the algorithm. Now we are going to learn analysis of algorithm. We have three cases to analyze algorithm. The first case is worst case, which means the maximum number of steps taken on any instance of size A. The second case is average case, which means the average number of steps taken on any instance of size A. The third case is best case, which means the minimum number of steps taken on any instance of size A. If you didn't understand these cases, then let's see an example to understand how to analyze algorithm. Here we have an array of 7 elements. Now we will analyze best case, worst case and average case by applying linear search to find any element. Linear search is a sequential search made over all items one by one. For example, if we search 19 in this array, we have to traverse from all elements until we reach 19. As we can see, 19 is the last element of the array, so it will take maximum number of steps to get search. This type of case is called worst case. And in the same way, if we search 34 in this array, it will take average number of steps to reach 34. So this type of case is called average case. But the best case is unique. Imagine if we want to search an element 15, which is already present as the first element in the array, then we will easily complete the search in first step only. So the best case means the minimum number of steps taken. Now we are going to learn asymptotic notations. There are 5 types of asymptotic notation: big O, big omega, big theta, small o, small omega. Big O. Big O notation represents the upper bound of the running time of an algorithm. Thus, it gives the worst case complexity of an algorithm. Here we have two functions f of n and g of n. F of n is equal to big O of g of n, which means f of n is less than equal to constant into g of n, where constant is greater than 0, n naught is greater than n, and n always tends to infinity. N naught means numbers. Do you know why we are learning these asymptotic notations? Actually, this notation doesn't show the how much time an algorithm will run. It shows the number of operation it will perform. It tells you how fast an algorithm grows and let you compare it with other algorithms. Now observe this graph. Here we have two functions f of n and g of n. Before and not, f of n can be greater than g of n, which means n naught is less than n. But after n naught, g of n is always greater than f of n, which means n naught is greater than n. Let's see few examples to understand big O notation. Here we have two functions f of n and g of n. F of n is equal to 3n plus 3 and g of n is equal to n square plus 2. You have to prove that f of n is equal to big O of g of n. To prove this, you have to make a growth chart and put different n values. Now observe this growth chart. Here we have three rows n, f of n and g of n. We have to put different values of n to get different values of f of n and g of n so that we can compare f of n and g of n. If n is equal to 1, then f of n is equal to 3 into 1 plus 3 is equal to 6 and g of n is equal to 1 square plus 2 is equal to 3. If n is equal to 2, then f of n is equal to 3 into 2 plus 3 is equal to 9 and g of n is equal to 2 square plus 2 is equal to 6. Later on, same continues with n is equal to 3, 4, 5 and 6. You can easily observe that initially f of n is greater than g of n up to n is equal to 3. But at n is equal to 3, g of n values comes closer to the f of n values. After n is equal to 3, for all n values, g of n is greater than f of n. Here you can observe correctly, there is a growth in g of n which is always greater than f of n. This is a non-linear growth of g of n. F of n is less than or equal to constant into g of n, hence we can say f of n is equal to big O of g of n, hence proved. Example 2. Here we have two functions f1 and f2. f1 is equal to 2n and f2 is equal to 20n. Both f1 and f2 are of same type of linear equation and are same in nature. In this question, we have to find asymptotic notations. To find the asymptotic notations, we again make a growth chart in which we have taken n is equal to 1, 2, 4 and 8. Where if n is equal to 1, f1 is equal to 2 into 1 which is equal to 2 and f2 is equal to 20 into 1 equal to 20. If n is equal to 2, f1 is equal to 2 into 2 is equal to 4 and f2 is equal to 20 into 2 is equal to 40. And same continues with n is equal to 4 and 8. You can easily observe in the linear growth chart that both f1 and f2 grows linearly. In this case, when we have linear growth, then we have to try to prove all possible asymptotic notations. Hence, we have two possible asymptotic notation. f1 is equal to big O of f2 and f2 is equal to big O of f1. Now we have to check which asymptotic notation is correct. To check which asymptotic notation is correct, we have to analyze constant values. If constant is greater than 0, then that asymptotic notation is correct. Now, f1 is equal to big O of f2. We can write it as f1 is less than equal to constant into f2. Now putting the values of f1 and f2. Therefore, we get 2n is less than constant into 20 into n. N gets cancelled out and we get 2 by 20 is less than equal to constant. Here you can observe that constant is greater than 0. Then we can say f1 is equal to big O of f2 is true. In another asymptotic notation, f2 is equal to big O of f1. We can write it as f2 is less than equal to constant into f1. Now putting values of f1 and f2. Therefore, in the same way, we got n cancelled out and we get constant is greater than equal to 10. Here we can clearly see constant is greater than 0. Therefore, f2 is equal to big O of f1 is true. Now the final conclusion is both f1 is equal to big O of f2 and f2 is equal to big O of f1 is true. Let's understand the basic concept of big O notation. Here we have two functions f of n and g of n. F of n is equal to big O of g of n, which means f of n is less than equal to constant into g of n, where constant is greater than 0, n naught is greater than n, and n always tends to infinity. Now try to understand the basic relation between two functions and big O notation. Here we have two functions f1 and f2. Now f1 is equal to big O of f2, which means f1 is less than equal to f2. In the same way, if f1 is less than equal to f2, then we can also say f1 is equal to big O of f2. Do you agree with me? If yes, then let's continue with another example. Example 3. Here we have two functions f1 and f2. f1 is equal to log n and f2 is equal to 2n. To find the asymptotic notation, we have to make a growth chart in which we have taken n is equal to 2, 4, 8, 16 and 32. We are taking these large values of n to sort the length of growth chart. Before solving these type of questions, you all must be aware of change of base formula. Log a base b is equal to log a base t divided by log b base t. By applying this formula, we can get all the values of f1 very easily. Here in the growth chart, you can observe a non-linear growth of f2. f1 is less than f2's growth. So clearly we can say f1 is equal to big O of f2 and f2 is equal to big O of f1 is wrong. Example 4. There are two functions f1 and f2. f1 is equal to 10n and f2 is equal to 2n square plus 5n plus 10. By the experience of previous examples, you all can easily guess f1 shows linear growth and f2 will show quadratic growth. Now here onwards, you all don't need to always make a growth chart of functions. Now we are going to apply a shortcut method. Step 1 is to drop the lower order terms and the step 2 is to ignore the constants. Here f1 is equal to 10n. 10 is a constant and gets ignored. Therefore the value of f1 is equal to n. Then f2 is equal to 2n square plus 5n plus 10. Here 2, 5 and 10 are constants. N is a lower order term, so all these gets cancelled. Then f2 is equal to n square. Here you can clearly observe f1 is less than f2. Therefore we can easily say f1 is equal to big O of f2. So this is the simplest method to prove asymptotic notations. Example 5. There are three functions f1, f2 and f3. f1 is equal to n, f2 is equal to 2n square and f3 is equal to 30 log n. We are again applying the shortcut method. Step 1 is to drop the lower order terms and step 2 is to ignore the constants. Now f1 is equal to n. Here we have no constants and no lower order terms, so we can say f1 is equal to n. f2 is equal to 2n square. Here we have 2 as a constant and there is no lower order term, so constant gets cancelled. Therefore we can say f2 is equal to n square. f3 is equal to 30 log n. Here we have 30 as a constant and there is no lower order term, so constant gets cancelled and therefore we can say f3 is equal to log n. By getting these values of f1, f2 and f3, we can say log n is smaller than n and n is smaller than n square. In the same way, we can also say f3 is smaller than f1 and f1 is smaller than f2. By these relations, we can say f3 is equal to big O of f1 because f3 is smaller than f1. f3 is equal to big O of f2 because f3 is smaller than f2. f1 is equal to big O of f2 because f1 is smaller than f2. Example 6. Here we have four functions f1, f2, f3 and f4. Now observe all four functions carefully. You can observe that there is a constant 1 in base of f2 and f4. Now cancelling those constants as we have done before, then we get f1 and f2 are of same form n to the power n, and f3 and f4 are of same form n to the power n plus 1. Therefore we can say that f1 is equal to f2 and f3 is equal to f4. We can also say that f3 and f4 is greater than f1 and f2. Now this is the point to be noted, the decreasing order of the growth. If you remember these growth values, then you can easily solve the questions. Now let's move forward. Big omega notation. Omega notation represents the lower bound of the running time of an algorithm. Thus it provides the best case complexity of an algorithm. Here we have two functions f of n and g of n. F of n is equal to omega of g of n. This means f of n is greater than equal to constant into g of n. Where constant is greater than 0, n naught is greater than n, and n always tends to infinity. N naught means numbers. Now observe this graph. Here we have two functions f of n and g of n. Before n naught, which means n naught is less than n, then g of n can be greater than f of n. But after n naught, which means n naught is greater than n, then f of n is always greater than g of n. This is all about big omega notation. Let's see an example of big omega notation. Here we have two functions f1 and f2. f1 is equal to 2 to the power n and f2 is equal to 2 to the power 2n. Here you can clearly observe 2 to the power n is less than 2 to the power 2n. So we can find two asymptotic notations. If f1 is less than equal to f2, then f1 is equal to big O of f2, and if f2 is greater than equal to f1, then f2 is equal to omega of f1. These two notations are possible here. Big theta notation. Theta represents the upper and the lower bound of the running time of an algorithm. It is used to analyze the average case complexity of an algorithm. In simple words, you can say big theta encloses of big O and big omega notations. Big O gives the worst case complexity and big omega gives the best case complexity. The combination of both big theta gives the average case complexity. The graph shows same as the definition is defined. Let's see an example of big theta notation. Example 1. There are two functions f1 and f2. f1 is equal to 3n plus 3 and f2 is equal to 100n plus 2. Both f1 and f2 are linear equation, so it will show linear growth. Now we have to prove that f1 is equal to big theta of f2. To prove this, we have to prove f1 is equal to big O of f2 and f1 is equal to big omega of f2. When f1 is equal to big O of f2, then f1 is less than equal to constant into f2. Now putting the values of f1 and f2, we get 3n plus 3 is less than equal to 100n plus 2. By solving this equation, we got n is greater than equal to 1 by 97. Therefore, f1 is equal to big O of f2 is true. In the other hand, when f1 is equal to big omega of f2, f1 is greater than equal to constant into f2. Now putting the values of f1 and f2, we get 3n plus 3 is greater than equal to 100n plus 2. By solving this, we get n is less than equal to 1 by 97. Therefore, we can say f1 is omega of f2 is true. If f1 is equal to big O of f2 is true and f1 is equal to big omega of f2 is true, then we can say f1 is equal to big theta of f2 is also true. Hence proved. Now we are going to study small o notation. Small o notation is the companion of big O notation. The big O notation says the one function is asymptotically not more than the another. To say that one function is asymptotically less than another, we use small o notation. The main difference between the big O and small o notation is comparable to the difference between less than equal to and less than. Now here you can see the big O notation is f of n is less than equal to constant into g of n, and small o is f of n is less than constant into g of n. So this is all about small o notation, and we have also compared the big O versus small o notation. Now we are going to see the last asymptotic notation, small omega notation. Small omega notation is the companion of big omega notation. The big omega notation says that one function is asymptotically not more than the another. To say that one function is asymptotically less than another, we use small omega notation. The difference between this big omega and small omega notation is comparable to the difference between less than equal to and less than. Big omega notation is f of n greater than equal to constant into g of n. But small omega notation is f of n is greater than constant into g of n. Now you can understand the key difference of big and small in asymptotic notation. Big asymptotic notation can be greater than equal to or less than equal to. But in small asymptotic notation, there is no chance of getting two functions equal. Now we are going to learn analysis of algorithm. Algorithms are of three types: normal algorithm, iterative algorithm, and recursive algorithm. Normal algorithm includes the normal operations like addition, subtraction, multiplication, division, or printing values. Iterative algorithm includes the uses of loops. The recursive algorithm consists of recursion. Let's take a close look of iterative algorithm. Example 1. For I is equal to 1, I is less than equal to 50, I plus plus, printf code with India. This loop will run maximum 50 times because I is less than equal to 50. So here the code with India is going to be printed 50 times. 50 is a constant value, so we can write it as 1. The complexity of this program is therefore big O of 1. Now let's take a view of example 2. Here, for I is equal to 1, I is less than equal to n, I plus plus, printf code with India. Here, this loop will run maximum n times. So the code with India is going to be printed n times. Therefore, the complexity is big O of n. Example 3. For I is equal to 1, I is less than equal to n, I is equal to I into 2, printf code with India. Here, incrementation of the value of I is equal to I into 2. I is initialized as 1. Here we are writing all the values of I. When I is initialized, its value is 1. We can write it as 2 to the power 0. When I is equal to 1, I is equal to 1 into 2, which we can write it as 2 to the power 1. When I is equal to 2, we can write it as I is equal to 2 into 2, which is equal to 4, and we can write it as 2 to the power 2. Same continues with other values of I. It goes up to 2 to the power k. K is the last element, last value of I. Now observe the second statement of the loop. I is less than equal to n. We can write it as 2 to the power k is less than equal to n. As we know, the last element of I is 2 to the power k. Now applying log on both sides, log to the power k is less than equal to log n. By solving this, we got k is less than equal to log base 2n. Now you can clearly say that the complexity is big O of log base 2n. Example 4. In this example, we have a nested loop. For I is equal to 1, I is less than equal to 500, I is equal to I plus plus. For j is equal to 1, j is less than equal to 2, j plus plus, printf code with India. Here, I value will go maximum 500 and j value will go maximum 2. Now, we can say code with India is printed maximum 1000 times. Now 1000 is a constant value and the complexity will be big O of 1. Example 5. In this example, we again have a nested loop. For I is equal to 1, I is less than equal to n, I is equal to I plus plus. For j is equal to 1, j is less than equal to n, j plus plus, printf code with India. Here we have I is less than equal to n and j is less than equal to n. By this we can say code with India will be printed n square times. So the complexity is big O of n square. Example 6. All the example before this was to show how to find complexity by just saying program or algorithm. But in example 6, you will learn to find complexity by summation method. Here we have a nested loop. For I is equal to 1, I is less than equal to n, I plus plus. This loop will run I is equal to 1 to n times. So we can write it as sigma I is equal to 1 to n. Now the another part of the nested loop is for j is equal to 1, j is less than equal to I, j plus plus. This loop will run j is equal to 1 to I. So we can write it as sigma j is equal to 1 to I. Printf code with India is a constant statement, so it is represented as 1 here. Now we got sigma I is equal to 1 to n and sigma j is equal to 1 to I into 1. We will solve this from right to left, means the red one will be solved first, then the yellow one. We can solve sigma j is equal to 1 to I into 1 by writing it as 1 plus 1 plus 1 up to upper bound minus lower bound plus 1. That is I minus 1 plus 1. Here the upper bound is I and the lower bound is 1. Plus 1 minus 1 got cancelled and we got 1 plus 1 plus 1 up to I times, which we can write it as I. Now we got the value sigma I is equal to 1 to n into I. If we put I is equal to 1, then the value is 1. If we put I is equal to 2, then the value is 2. If we put I is equal to 3, then the value is 3. Therefore, we can write it as 1 plus 2 plus 3 plus 4 up to n times. This is the sum of n terms, and the formula of sum of n terms is n into n plus 1 by 2. By solving this formula, we can get n square plus n by 2. And as our shortcut says, constant and lower order terms get cancelled, so we have cancelled the lower order term and constant. Therefore, the complexity is big O of n square. Example 7. Here we again have a nested loop. Let's see it. For I is equal to 1, I is less than equal to n, I plus plus. By solving the previous examples, you can easily guess the complexity of this loop is n. Then for j is equal to 1, j is less than equal to n, j is equal to j into 3. This loop is similar to example 3 as it gives the same type of complexity. In example 3, we have I is equal to I into 2. So we get the base as 2. But here we have j is equal to j into 3. So the base of log is 3. The final complexity of the nested loop is big O of n log base 3n. Now let's see an example 8. For I is equal to 1, I square is less than equal to n, I plus plus, printf code with India. Here I square is less than equal to n. So we can write I is less than equal to root n. Therefore the complexity of this code is big O of root n. The next type of algorithm is recursive algorithm. Recursive algorithm consists of recursion. Example 2. Here we have to find the recurrence relation of the program. Void f of int n. If n is greater than 0, the loop will run for I is equal to 1, I is less than equal to n, I plus plus, printf code with India, f of n minus 1. F of n minus 1 means n will be decremented from the function f. If f of n will take t of n times, then f of n minus 1 will take t of n minus 1 time. Here code with India will be printed n times. So now we can say t of n is equal to n plus t of n minus 1. Example 3. We again have to find the recurrence relation of the given program. Void f of int n. If n is greater than 0, then the loop will run for I is equal to 1, I is less than equal to n, I is equal to I into 2. Printf code with India, f of n minus 1. In previous example, we have solved this loop. This loop will give log n complexity. Here, f of n will take t of n time and f of n minus 1 will take t of n minus 1 time. So the recurrence relation is t of n is equal to t of n minus 1 plus log n. The PDF note of this video is available on the link in the description. To know what you have learned from this video, do attempt the quiz present in the description. Thank you so much guys for watching this video. Do like, share and subscribe my channel.